All right, so we're going to talk about the Henderson Hasselbalch equation today. Oftentimes it's even called Henderson Hasselbalch, which sounds way more cool than, I don't know, I can't use it. I'm not that cool. So we are going to start by showing you the derivation. So it's actually a derivation from a simple equilibrium constant. So if we have some reaction with an acid, so HA, some kind of weak acid, it's in equilibrium with H plus and A minus, its conjugate base, we would write an equilibrium constant as Ka is equal to H plus times A minus all over HA. Now, this is a standard equilibrium constant, A, coming from the fact that it's an acid breaking apart in equilibrium. Now, to derive the equation is actually relatively straightforward. So what we're going to do, we're going to first take the log of both sides. So we'll have the log of Ka is equal to the log of H plus concentration times the A minus concentration all over that of the initial acid concentration. Now we can separate this even further and break off just the H plus. And we'll see why in a little bit. So anytime you have a log of something times a log of something over here, essentially you add them together. So I have log of H plus the log of the A minus over the HA. And now if we switch these two to get the H plus on one side, we have negative log of H plus equaling the negative log of the Ka plus log of the A minus over HA, where A minus is the conjugate base again, and this is the initial acid. Now, oftentimes you see the notation P. P essentially means negative log of. So here we can take this negative log of and substitute it with a P. And here we take this negative log of and we substitute it with a P. And what you get is pH equals pKa plus the log of the concentration of the base over the concentration of the acid. And this is the equation. So why we even use this equation actually makes things really, really easy to figure out. So it's helpful to understand logs. So if we have something like log of 10, log of 10 equals 1. Essentially, it's the number of zeros after the 1. It makes it really, really, really easy. So the log of 100 equals 2. The log of 1,000 equals 3. And be careful here, this is log. This is not natural log, where you'd have to take an inverse of e to the negative. All right, so this is not natural log, so be careful you're making sure you're using log in your calculator when you're calculating these. So why this is important? Well, let's say you've got a pH that you want to buffer to, so you want a certain pH that you want. So you want a particular pH, and you know the pKa of the acid. Well, in order to get that pKa, you just pay attention to the logs. So for example, if I had a pH of 6, or let's say I want a pH of 7, but I have a pKa of 6, what proportion of base to acid do I need? Oh, well, I need a proportion of 10 over here, because 6 plus 1 equals 7. In other words, I need a proportion of base over acid to be 10. And so that now tells me I need 10 times the base, then I do acid. So it's a really, really quick way to utilize information and figure out what specific acid-base concentration you need to get a particular pH. Equal sign there. All right. So in class, we had this quiz. There we go. Where we used Henderson Hasselbalch equation and essentially attempted to figure out a problem. Well, it says find the pH of a solution of sodium hypochlorite. It gives you the pKa and tells you it's got a base acid ratio of 0.47. Right away, I know that there's more acid than there is base because it's a decimal point. If there's more acid than there is base, then the pH better be lower than the pKa. So we know that it's over base over acid, and now these can actually be concentrations or moles, assuming they're in the same solution, which they ought to be. So you can use it in mole per liter or moles. That's because the liters will eventually cancel. And so all we do is a plug and chug with this. We don't know the pH, that's what we're solving for, but we know the pKa is 7.53 plus the log of the base over acid ratio, which again, there's more acid than there is base because we're talking about a decimal point, so the denominator had to be bigger. And if you calculate this out, you get an answer of 7.2. You do the same thing with the next problem. It's a similar acid-base question. The only difference is it gives you things in grams. So this is find the pH of 1 liter of buffer solution made from, oh, I forgot. We added an additional 12.43 grams of tris, which is a really common base, especially in biology, and 5.67 grams of tris hydrochloride, which would be the acid. So this one's the acid, this one's the base. And we're looking for the pKa. Well, again, we know pH equals pKa plus the log of the base over the acid. And one of the first things I do anytime I read a problem is if I have grams, I immediately turn that into moles. So here I would say 12.43 grams. Try to keep track of what you're talking about. This is our base. So 12.43 grams divided by 121.135 grams per mole. And I get an answer of 0.1026 mole. Let's keep a couple extra sig figs. Actually, just the right number of sig figs. We do the same thing with the acid. Where we got 5.67 grams, dividing it by 157.596 grams per mole. And you get an answer of 0.03598 mole. All we do is plug and chug. We know the pKa is already 8.072. We now know the number of moles of our base divided by moles of our acid. Again, you could have taken each of these and divided it by 1.00 liters. But when you put one over the other, the liters are going to cancel anyways. So it doesn't matter if you just keep moles. So here we're going to put base, which is 0.1026, divided by our acid, 0.03598. We have more base than we do acid, so we should expect this answer to become more basic. And we get an answer of 8.53. And that's how we use Henderson Hasselbalch.